Okay, class, welcome from Atlanta. What I'm going to do today, this is going to be tomorrow's lecture, and what this represents is I'm going to do a worked answer key for a worksheet that I'm going to send you once it is done. So we're just going to go ahead and start here. This is all review of things we've covered in class already. Acids and bases can be a tough topic for folks, and we'll actually do a buffer thing at the end as well. I really recommend you practice this. Try to do them without my help. I'll post an answer key as well, but make sure you know how to do all this stuff. Okay, so phosphoric acid is the formula HPO4. It's triprotic acid, meaning it can lose 3 H pluses. The phosphate anion has a charge of -3. Write a balanced equation showing excuse me, the reaction of phosphoric acid with potassium hydroxide to produce potassium phosphate in water. So what's going on here is we're reacting with enough potassium hydroxide to completely react with all 3 protons. So we're going to go ahead and do that. So that's HPO3, that's aqueous. This is a weak acid. It's not one of the strong acids we were supposed to memorize. It's going to react with potassium, potassium hydroxide, so KOH. And I'm going to need 3 of them, one to react with each of those protons. And then KOH is a strong acid, so this is not going to be a strong base. KOH is a strong base. This is not going to be in equilibrium. It's going to react to make 3 waters. Right, 3 hydroxides reacts with 3 protons to make 3 waters, plus to make a potassium. We have to have 3 potassiums to have it balanced with what's above before, also to neutralize this -3 charge, PO4, and that'll be aqueous. All right, so that's if we had that fully react. I also wanted you to practice what was on the problem on the quiz. A lot of people did fine on it, some people not so much. And I said, now write out all 3 individual reactions. So let's assume that we add one equivalent of hydroxide, and then another equivalent of hydroxide, and then another equivalent of hydroxide. These acids, it's easiest to pull off the first proton, then the second, then the third, so they will come off one at a time. And so what this would look like is we'd have start with our phosphoric acid, and that would react with one equivalent of KOH. KOH is strong base, so it'll fully react, and that would give us one KH2PO4 aqueous plus 1 water. Okay, then our KH2PO4 aqueous can react with another KOH. That's KOH is still a strong base, so then we're going to get K2HPO4 aqueous plus another water. Okay, and then finally we'll have our K2HPO4 aqueous, and that's going to react with a KOH aqueous, and that's going to give us a K3PO4 aqueous plus a water. Okay, those are our reactions that we would we'd write out right there, and if you add them together, which I'm not going to do here, it'll give us that reaction up at the top. All right, let's go on to our next one. How do the H plus and OH concentrations change when an acid is added to water? Well, if you add an acid to water, right, an acid dissociates. We think about HA goes to make H plus, right, plus A minus in water. And so what's going to happen is our H plus is going to go up. So we can talk, well, maybe not an arrow like that. Let's say for A here, H plus increases, OH minus decreases. All right, that H plus increases is obvious from this equation, and then what you need to remember that we have this constant for the equilibrium of water, Kw, is equal to 1.0 times 10 to the negative 14th. Look, that'll be on the top of your quiz if you need it. Times the concentrate, or that's equal to the concentration of H plus times the concentration of OH minus, like that. And so based on this equation, this has always got those two multiplied times each other has always got to be equal to 1 times 10 to the negative 14th. And so if this goes up, then that's got to go down for this number here to be the same. Okay? And so then by the same method, a base is going to produce OH in water. And so if the OH minus is going to increase, and if the OH minus increases, then H plus is going to decrease. Decreases, increases. Okay? Next question. Which has a lower pH? A 1 times 10 to the negative 4th solution of HCl, which you should hopefully recognize as a strong acid, or a 1 times 10 to the negative 4th same concentration solution of HCO3. So this is carbonic acid. It is not one of our strong acids we need to memorize. So it's not a strong acid. So this one fully dissociates in water. So what that means is that if we write it out, HCl goes to H plus Cl minus, and we can think about it being 100% this. All right, which means that my concentration of H plus is going to be that. And if you do your negative log of pH, or of the H plus concentration, I can do this one in my head, the pH is going to be equal to 4, okay? Because exponent. This one is a weak acid, does not fully dissociate. Okay, so what that means is we're going to end up, if we have H2CO3, I should have done my aqueous over there, I didn't. There's going to be an equilibrium. It's going to go to make H plus HCO3 aqueous, that'll be a minus, that's bicarbonate. That's part of baking soda. Is also aqueous. Aqueous. There, I feel better. All right, so, but this does not fully dissociate. So what that means is that this is going to be, it's going to be mostly this, and it's going to be less than probably 5% if you need a number for it, less than 5% of this. And so there's going to be less of this than over here because we started with the same amount, and less means a higher pH. Okay, so which has a lower pH? If I was to go back up here and kind of erase some of my stuff, this one or has a lower pH. Lower pH. Okay, next problem. Calculate the pH for each of these strong acid solutions. So these are all strong acid solutions. They're going to fully dissociate water. So A, my H plus concentration, HClO goes all the way to dissociation, so it all becomes H plus and ClO4 minus, so my H plus concentration, and it does that in a one-to-one way. All of these do this in a one-to-one way. So this is going to be HClO4, we'll do my aqueous, we'll go back down, there we are, HClO4 aqueous, is going to fully dissociate to make H plus ClO4 minus. All of these have, do you see how they all have one proton in front? So they're all going to react. One of these makes one of these. And so for A, my H is because these are strong acids, that concentration is going to be equal to 0.27 molar. For B, the H plus concentration, it's going to fully dissociate. It's going to be equal to whatever the concentration of this acid is equal to 0.035 molar. C is going to be equal to 5.3 times 10 to the negative 3 molar. And if you remember, our equation for pH is negative log of H plus concentration. So what I can do is I can either put this here, or that there, or that there. If I take my calculator and I put 0.27 into it, and then I take the negative log of that, I take the log and I take it times negative 1, I get a pH of 0.05, I'm sorry, not 0, 0.57, okay? If I do B here, I'm going to clear my calculator, I'm going to put 0.035 into it, and I'm going to take the log, and my pH ends up being, let's go pH equals, this is going to be 1.46, and over here pH equals, and this is going to be my last one, I'm going to put in 5.3 to the 3. I think we've worked out all the people, I hope we've worked out all the people that are having problems with the EE key with their calculator. We've learned how to do that, but put this in, make sure you've got it. So I put 5.3 in times 10 to the negative third, or on my calculator it's 5.3 EE negative 3, or EE is the EE key. And then I'm going to go ahead and take the log of that, and I get a pH of 2.28. All right, next problem. Trifluoroacetic is a weak acid. Construct an ice table and find H plus concentration for that. All right, well, let's go ahead. We have some room. I'm going to reclaim it. There we go. All right, so this is one of those things where we start with a weak acid. We have all acid, and so we need to figure out how much it dissociates and what the concentrations of things are. Well, actually, this just wants us to figure out, oh, it does want us to figure out the pH. Well then, that doesn't make me happy because of the next question, but let's go ahead and just do the ice table here. So I've got hydrofluoric acid, right? And that's going to go ahead and react to make H plus. I'm just rewriting, but I'm about to do my ice table underneath it, plus C2F3O minus. Okay, we'll do it like that. And then what we have is we have our initial, our change, and our equilibrium concentrations. Our initial is 0.150 molar, and then we're going to have 0 that and 0 that. And then that reacts, and it has to go to the right because there are zeros over there. And so we're going to get a change of some of it's going to go away, and for every trifluoroacetic acid that goes away, we're going to get 1 H plus, and we're going to get 1 trifluoroacetate is what this would be called. And then our final concentrations are going to be 0.150 molar minus X, and it's going to be plus X, and it's going to be plus X. And then I'm going to go ahead and give us some more space down here to do the rest of our problem. Okay, maybe one less. But I actually want to come down here first and ask my next question. Okay, so can you use the simplifying assumption for the problem, Robert? Do you need to keep all the x's and use the quadratic formula? Well, my Ka is 0.3 and my pH, or my concentration is 0.15. So if you remember, our rule here is that the concentration of my acid has to be greater than 400 times whatever my Ka is, right? So if we look at that ratio, our acid concentration up above was 0.150 molar, and our Ka was 0.3. Let's take a look at that. Let's make sure I got those right. Okay, and I do. And so, I think you can look at this. I can put this into my calculator, but what I can tell you it's going to be is that's 1 over 2. Okay, and 1 over 2 is not greater than 400. It's 1/2. And so we're going to have to do the quadratic formula. So that's why I was disappointed when I started working and realizing that this problem was asking me to go all the way to figuring out the pH. So we're going to go ahead and use the quadratic formula here. You will not have to use the quadratic formula on a test. If you had to do this all the way to pH, you wouldn't need it. But I might ask you to tell me whether you can make the simplifying assumption or not. So here we can't use it. So what that means is when I set this up, I'm going to have Ka is going to be equal to my H plus concentration times my trifluoroacetate concentration. I feel like I've lost an oxygen there. Divided by my concentration of the trifluoroacetic acid. Okay, and so let's go ahead and put our x's in. So H plus is x. That's going to be times the acetate is x. And on the bottom, now I have 0.150 minus x. And that's going to all be equal to 0.30. Okay, now we need to do some algebra. And I haven't left myself a ton of space. Let's see if I can make a little space. Hopefully not mess up what I done earlier. And so what I get then is if I can multiply this bit here times both sides. If I multiply that bit times both sides, I end up with, we'll come down here, I have x squared for x times x, and that's going to be equal to, all right, so let's actually do this. I'm going to multiply the top by 0.150 minus x. And so that's going to cancel with that, but I also have to multiply this 0.150 minus x. And I have to distribute that, so I'm going to multiply this times that and this times that. So I'm going to go ahead and do that right now. 0.3 times 0.150, and that's 0.5, 0.045. Okay, that's the number part, and then the other part is minus 0.30x. I'm going to put this into the quadratic formula. What I need to do then is I need to get everything on one side so it is it's equal to 0. So I'm going to subtract this from both sides, and that will give me x squared minus, actually plus, I'm going to have to add this to both sides, right? Let's go ahead and write it out. So I'm going to add plus 0.30x, and I'm going to go minus 0.045. Okay. I'm going to go ahead and just pull that down. Well, actually, I'll write it over here after all. Plus 0.30x and minus 0.045. And so what I get out of that is x squared, if I rearrange it just a little bit, plus 0.30x minus 0.045. We're going to need to put this into the equation for the quadratic formula. So this is A, this is B, this is C, and I'm not going to have you do this on a test or a quiz or anything like that. I'm going to write these numbers down and I'm going to tab out. I'm going to hope to not lose my video capture, and we're just going to use a formula calculator off the internet. So A is going to be 1, B is going to be 0.30, or just 0.3, and C is going to be negative 0.045. All right, let's see. All right, I'm still recording. Quadratic formula. There we go, quadratic formula calculator. All right, calculator soup. It's soup. Okay, my value is 1, my B is 0.3, and my C is negative 0.045. Right. We're going to calculate. Working. All right, there we go. And so our answers are either this it looks like 0.110. We only have two significant figures, so 0.11, or it's that negative number. There's no such thing as a negative concentration, so it is not the negative concentration. This is not that. Okay. So it's not the negative concentration, so it's got to be the 0.11. So my answer is my H plus concentration is equal to X, which is equal to 0.11 molar. I can then put that in my calculator. So pH is equal to the negative log of my H plus concentration, or 0.11. And that is going to be equal to 0.11 log, and I get a pH of 0.96. Okay, and there's that one. All right, so you need to be able to set up an ICE table. You need to be able to recognize whether you can use the simplifying assumption or not. You will not need to do the quadratic formula on a test or something like that. But if you ever need to, you can always you can either look it up and do it, or you can just use some online calculator like I just did. All right. So we answered that we can't use the simplifying assumption. Now we're going to move down to the next problem. Hydrogen peroxide is weakly acidic. Construct an ICE table and find the H plus concentration, the pH, and the percent ionization. We haven't done percent ionization before, but we know how to do percent, so that shouldn't be too bad. I'm going to try to set up my ICE table right here so I don't have to write as much. ICE. We start out with a hydrogen peroxide solution of that. Hydrogen peroxide, this is the same hydrogen peroxide you would use to like bleach something, like your hair maybe. This is 1.20 molar. We're going to start with 0 of the other two. Because we have zeros, we have to go to the right, so some of this is going to go away, and for every hydrogen peroxide that goes away, you see we only lost one proton here, so we're going to make one of these and one of these, and so my final concentrations are going to be 1.20 molar minus X and X and X. Now we need to see whether we can make our simplifying assumption. So we have 1.20 molar, right? Remember, it has to be the ratio of the acid concentration to the Ka needs to be over 400. 2.4 times 10 to the negative 12th. You can put that in your calculator, but that is much, 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 much greater than 400. So we can make our simplifying assumption, and we can get rid of it. And just put it in your calculator. It's going to be some huge thing times 10 to the 12th, or it'll be times 10 to the 11th. Huge number. All right, so we know that our Ka is going to be equal to 2.4 times 10 to the negative 12th, and that's equal to our peroxide concentration over oh wait, no, our peroxide concentration is a reactant. That goes on the bottom. Our H plus concentration times our HOH2 minus, our peroxide base concentration, whatever you call that. I'm sure an organic chemist could tell you that. I'm not an organic chemist, but I've seen them played by actors on TV. And what that's going to be equal to then is we have x and x right on top, x times x, and on the bottom we got rid of our x, so now it's easier to calculate, and that molar. So I'm going to bring it down and get rid of the stuff in the middle. If I take 0.120 molar times this and 1.20 molar, so I multiply 1.2 molar times both sides, I'm going to end up with 1.2 times 2.4 to the negative 12th. And I've got, on the bottom here, I've got or I'm going to write my new line here actually. 2.88 times 10 to the negative 12 is equal to x squared. All right, and so to solve for x, I need to take the square root of that. 2.88, clear it from my calculator, put it back in, hit the square root key, and I got to count decimal places because my calculator is not scientific notation. 1, 2, 3, 4, 5, 6. That's going to be 1.6. Let's go 1.70 times 10 to the, was that 6? I forgot already. 1, 2, 3, 4, 5, 6. It is 6. 10 to the negative 6th is equal to x. X is equal to my H plus concentration. Okay. And my pH is equal to my negative log of H plus concentration, which in this case is 1.70 times 10 to the negative 6th. I'll go ahead and put that in my calculator. 1.7 to the 6. What the heck is that? Log. Okay, and that tells me the pH is equal to 5.77. Okay, that's one of my answers. My other answer was the ice table, right, because it asked for that. And then it wants the percent ionization. All right, so what we're saying, the percent ionization is how much of this stuff dissociates. Well, percent is equal to parts over whole, right, times 100. Well, x is how much dissociated. So I've got 1.7 times 10 to the negative 6 over 1.20 times 100. It's going to be a super small number. 1.76 negative divided by 1.2 times 100. And my percent is 1, 2, 3, 4. 1.4 times 10 to the negative 4%. Super small. All right, so it's really not very relevant. This is also another reminder that this is so small that our simplifying assumption was okay. All right, great. Let's go do the next one. Oh, this is our last one, too. All right, so let's go ahead and do this. Solution initially contains 1.2 molar Na4Cl. It reacts with 0.3 moles of OH, which converts some of the NH plus to NH3. Prepare a table. We didn't do this one in class, did we? Am I giving you one we've done in class already? Hold on. I want my short-term memory back. Okay, so it feels familiar. Okay, so this is kind of what we did last year, right? So we're trying to get control of our notes. Nope. 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 Maybe I did this I think I did this practicing with people in the for the help session last Thursday. So sorry, those of you that were at the help session. We're going to look at this one again. All right, so prepare a fire table. So now we need to figure out how things change. So we're going to go ahead. First, I need to write out the reaction here. So I've got a solution that contains NH4Cl, and that's going to react with hydroxide, OH minus, and that's going to make, it's a strong base, and so that's going to make, it's going to turn that NH4, it's going to take a proton away from it, it's going to make NH3, and that's going to make water. Okay, and so we've got our fire table. What is it? First reacts end, I guess that's what it is. Anyway, so we start out with 1.20 moles of this. It reacts with 0.30 moles of this. And we start out with that much of this. We don't have any of this. We don't, well, we'll make some water. We won't worry about that. Let's not worry about the water. The water's 55 molar. It's not going to matter. We'll just not worry about the water. But, and then I think we put there was a CL here. Gosh, I feel like I worked this. But anyway, in class. But, so then, how much reacts? Well, we're going to have the smaller of these two reacts. I'm going to have negative 0.30. That's going to react because that's all that can react. These react 1 to 1. And then I'm going to end up with plus 0.3 of this because for every one of these I have, I get one of these. And then our final equilibrium concentrations are going to be 0.90 moles, not concentrations, 0 of this, and we're going to end up with 0.30 moles. Okay? So now, what we can do, so we figured out, we did our fire table, right? How many moles are present after the addition of the hydroxide? Well, we solved for that, right? It's this many and this many. Okay, we did the fire table, that was part of that. And now we do the Henderson-Hasselbalch to figure out what the pH of the solution is. This is the lovely part of the Henderson-Hasselbalch equation. So we need to think about which is this is the acid, which is this is the base. That's the acid. That's the base. And plus we got a pKa here. Okay, let me erase that a little bit so we can see it. We got this pK there. Okay, and so now we know that our Henderson-Hasselbalch equation is, and I'll give this to you on a test. If I forget to give it to you, you need to ask for it. Plus log of A minus, that's our conjugate base, over our acid. Okay, and that's going to be, we have our pKa is 9.25 plus the log of A minus, which is going to be 0.30, right? That's our conjugate base over our acid, which is 0.90. These are moles and not molar in terms of concentration, but since they're in the same volume, I can use the mole ratios instead of the concentration. And so then I can put this into my calculator. 0.3 divided by 0.9 is going to be 1/3. I'm going to take the log of that, and I'm going to add that to 9.25. And what I get is a pH of 8.77. Okay? Well, I hope you have enjoyed the lecture if you've been watching it. I hope you're happy. It's 35 minutes instead of a whole hour, so you get out a little bit cheap here. I hope you've been working the problems, which, you know, is not getting out cheap, right? It's going to have taken you a while to work this. But hope that went well, and if you have any questions, please reach out to me. I would be happy to try and set up a Google Meet while I'm out of town. And you guys have a good week, okay? Or have a good Monday, and I'll post more stuff soon.